You know, large language models are absolutely incredible, but they have one, well, giant problem. They're huge. So if you want to run them on your own computer with total privacy, you've got to shrink them first. Today, we're going to dive into the most popular way to do exactly that, a technology called GGUF. It really is the key to solving this massive puzzle.
And just to give you a sense of scale here, a really powerful model like DeepSeek can be a staggering 700 gigabytes. I mean, that's more storage than a lot of laptops even have, let alone the memory you'd need to actually get it running. So that brings us right to the main problem, doesn't it? How on earth do you take that 700 gigabyte behemoth and get it to work on your personal computer? Well, the answer is a process called model quantization. And check this out. This shows you just how incredibly effective it can be. Using GGUF quantization, that very same 700 gigabyte model can be squeezed all the way down to a much more manageable 10 gigabytes. That is a massive reduction, and it's what makes running it on your own machine possible. So how does this magic actually work? Now here's where things get really interesting. The official documentation for this stuff is, well, it's sparse, to put it mildly. One of the authors famously said they just don't like writing papers and don't see a reason to advertise. And you know what? That's why we have to do a little bit of reverse engineering to piece together how this amazing technology really works. So let's start at the very beginning with the first generation legacy quants. And even though they're older, they are the absolute foundation for everything that's going to come next. You have to understand these first. The core idea here is called linear quantization. Now, a model's weights, that's just all the numbers it learned during training. It's what holds all its knowledge, and there are billions of them. Quantization is kind of like taking that huge continuous spectrum of numbers and sorting every single one into a fixed set of bins or buckets. We're trading away a little bit of perfect precision for a much smaller, way simpler representation. So these legacy quants came in two main flavors. Type 0 is symmetric. It just assumes your numbers are all nicely centered around 0. But of course, if they're not, you end up wasting some of your precious integer bins. Then there's type 1, which is asymmetric. It's more precise because it uses the full range of numbers, but the catch is it needs to store an extra value to keep track of where the real 0 is. It's a classic trade-off, right? Simplicity versus efficiency. But here's the problem. Those constants, the scale and the 0 point, they have to be stored for all these little blocks of weights. And when you add it all up for a big model, you could be using 2 gigabytes of storage just for the constants. That is a huge overhead, and it totally sets the stage for the next big innovation. And this brings us right to the second generation, K-quants. They were designed specifically to solve that massive overhead problem, and they did it in a really clever way. The solution was almost deceptively simple. Hey, if the constants are too big, why not just quantize the constants themselves? It's basically a two-level system. First, you quantize the model's weights like before. Then you group the resulting constants into these superblocks, and you quantize them to an even lower precision. It's called double quantization. Pretty smart, right? And the result? Whoa. It is dramatic. For that same 16 billion parameter model we were talking about, the overhead for the constants drops from 2 gigabytes all the way down to just 1 gigabyte. They literally cut the storage cost in half with this one simple trick. Okay, so this leads to a question that trips up a lot of people, even some of the AI assistants out there. What does that K in K-quants actually stand for? The most common guess you'll see online is K-means clustering, but that is wrong. K-means is a totally different technique that's used in the next generation we're about to talk about. The truth is, nobody knows for sure, but it most likely comes from clip², which is the last name of the developer who created it, or maybe kernels for the new CPU code they had to write. And that brings us to the third and latest generation, I-quants. And listen, this isn't just a small improvement on the old method. It's a complete conceptual shift in how to even think about quantization. Okay, so instead of looking at each number individually, I-quants use a technique called vector quantization. Imagine a library. Instead of describing every single word in a book, you just find the book that's closest to what you're looking for and you write down its library code. I-quants does something really similar. It groups weights together, finds the closest reference group in a predefined codebook, and just stores the code for that reference. Now, the crucial point here is the incredible compression rate you get. For a group of 8 weights, you only need to store an 8-bit code for the reference vector and another 8 bits just to remember if they were positive or negative. You do the math, and that works out to a mind-bogglingly efficient 2 bits per weight. Okay, now at the same time I-quants were introduced, Another really powerful feature was added that can actually be applied to any of the quantitation types. It's called the importance matrix. And the idea is really simple and intuitive. Not all numbers in a neural network are equally important. It just makes sense, right? Some of them have a much bigger influence on the final output. The importance matrix is what identifies these critical weights so we can treat them with a little extra care. So how does it work its magic? Think of it like a photo. Normally, you'd use the same filter to both shrink the photo down and then blow it back up again. But with an importance matrix, you use a special, smarter filter when you blow it back up. This new filter knows which parts of the photo are most important, like a person's face, and it makes sure those parts are reconstructed extra sharp, improving the overall quality with zero extra file size. Okay, so we've covered legacy, K, and iQuants, plus the importance matrix. Now it's time to put it all together and finally learn how to decode those confusing GGUF file names you see everywhere. First thing you'll notice are letters like S for small, M for medium, or L for large at the end of a name. This is all about mixed precision. It means that even in, say, a 4-bit quantized model, some of the most critical weights are actually kept at a higher precision, like 5-bit or 6-bit, just to preserve the model's quality. So let's break down an example, like Q4_K_M. The Q4 is easy. It tells us the mean quantization is 4-bit. The K tells us it's using the second-generation K-quants, the one with that double quantization trick. And the M tells us it's the medium variant, which means it uses a healthy amount of those higher precision weights for the really key parts of the model. See? You can now read any of these names and know exactly what's under the hood. So, now you have the tools. You can understand the trade-offs between size and quality and the underlying technology. Which brings us to the final question. Knowing everything you know now, which quantization method are you going to pick for your next project?